Comparing and contrasting linked lists and trees. Hello, everyone. Today we're going to explore two fundamental structures, linked list and trees. So our goal is to understand not only how they are different, but also understand how each serves its unique purposes in solving various computational problems. So by the end of this lecture, you should be able to have a better understanding of how these two structures are different and understand their pros and cons and decide when to use one over the other in your project. Basic definitions. So let's start with the basics. A linked list is a linear collection of elements called nodes. Each node contains data and a reference to the next node in the sequence. So this creates a chain-like structure, and linked list can be singly, doubly, or circularly linked list. And they each offer different advantages in terms of navigation and efficiency. On the other hand, a tree is a hierarchical data structure. So it's similar in the sense that a tree is also made up of nodes, and where each node has a value and references to child nodes. I guess the difference between the linked list trees is that trees are not linear. So the top node, called the root, branches out to child nodes, which in turn may have their own children. This creates a multi-level structure, and common type of tree is binary tree. And for binary tree, each node has at most two children. Structural differences. So if we kind of delve into structural differences, we can see that linked lists and trees are quite different. So in a linked list, each node is connected to in a single line, and there is no concept of hierarchy or levels. It's simple but effective for certain types of data manipulation. Trees, however, are inherently hierarchical, so they consist of multiple levels with the root node at the top and leaf nodes at the bottom. This structure allows for efficient organization and retrieval of data, thereby mimicking real-world hierarchies like family trees or organizational charts. Memory allocation. So both linked lists and trees utilize dynamic memory allocations. What we mean by that is the memory for nodes is allocated at runtime, and this allows these structures to grow and shrink as needed. And this dynamic nature makes them flexible and powerful for handling data whose size might not be known in advance. Access patterns. So in a linked list, access is sequential. So if you want to find an element, you need to start at the head and follow the links until you find the desired node. This can be time-consuming for large lists. Trees, on the other hand, offer a more efficient access pattern, especially if they are organized in a specific way, like in binary search trees, which we will learn later. And in such trees, each decision at a node cuts the search space in half, significantly reducing the time it takes to find an element. Use cases. So linked lists are great for situations where you need a simple dynamic collection of elements. They are particularly useful for implementing queues and stacks and for applications where memory efficiency is important. Trees are used for representing hierarchical data, so they're used in databases for indexing, compilers for syntax trees, and used in algorithms for efficient searching and sorting. So the structure of a tree makes it ideal for scenarios where data is naturally hierarchical or needs to be accessed in a sorted manner. Performance considerations. Performance is really important factor when you want to choose a data structure. So for linked list, we know that search operations are linear in time. This means that as the size of n gets bigger, it can be slow for large data sets. However, adding or removing elements is very efficient, especially if you are working at the end of the list or have a reference to the node that you want to remove or add. Trees, what's good about trees is that it offers a logarithmic search time, especially in balanced trees, which we'll go over later. It makes them much faster for search operations than linked lists. However, the complexity lies in maintaining some of these types of trees, such as AVL or red-black trees. It can be more complex due to the need for rebalancing after insertion and deletions. Complexity and learning curve. So linked lists are generally simpler and more straightforward, making them an excellent starting point for somebody who kind of started in data structure. Trees, since trees have various types and balancing rules, they can be more complex and often require a deeper understanding of algorithms and recursion. However, mastering trees help you with array of possibilities in terms of efficient data storage and retrieval. In conclusion, while both linked lists and trees are essential data structures, they each have their unique characteristics and best use case scenarios. So the choice between using a linked list or a tree depends on the specific requirements of your application, such as the type of data you're dealing with or the operation you need to perform frequently and the efficiency you need to achieve in terms of time or space. Thank you, everyone.